Hello, it's Keith here, and this is lesson 51 of the platform-specific series of my 68000 assembly programming tutorials, and we're back on the Amiga today. We're looking at Mintile again, and this is the alternate version of the code that I wrote. Now, this is using the blitter to draw the tiles to the screen. Now, unfortunately, it's actually a bit slow. It's really, I would say, too slow to actually be practically usable. Now, when I started writing it, I was writing it with warp speed enabled, as you can see here, and it looked pretty good, but then when you actually come to use it, you find it's not really a suitable speed for a real game. However, I still think it's worth looking at because the blitting mode, the blitting capability of the Amiga is very capable, and it's also quite complicated in some ways. And so I thought looking at this as a practical example of trying to get the blitter to do what I wanted rather than just trying to get it to do anything in some cases, I thought was still worth looking at. Now, this is Mintile, and I'm already working on the replacement for Mintile, which is a more advanced version called Maxtile, and I won't be using the blitter for that. It's clearly too slow for these small tile movements, so I will be coming up with some more advanced bit shifting software code to draw directly to the screen memory. I should point out that the fact that this example is too slow is simply because this example works entirely in 8x8 pixel blocks. Like most systems that have hardware graphical routines for acceleration, in the sense of being able to copy blocks of data and things, the larger the block, the more efficient it is. So if you are moving a very large area, often that will take the exact same amount of time or very similar amount of time as a very small area. And so because we're breaking up our large sprites into small 8x8 blocks, it becomes very inefficient. Unfortunately, it's simply the way this code works isn't suited to the way the blitter works. But this series is all about making all the systems do the same thing, so that's what this has ended up doing. I have actually tested it. Basically, the reason the code is so slow is because there's a check before we tell the blitter what to do next. We have to make sure that the blitter has actually finished its last job, and basically it never has. So we're just constantly stuck in these wait for blit loops here, these things here. These are taking up all the time. If you disable it, then the new settings for the next blitting job get sent, and they actually overwrite the ongoing job of the blitter, and that means that the blitter starts malfunctioning. So we're stuck. We can't start doing the next job. We've got to wait for the last job, and the last job's never finished, and so the software is actually being slowed down by the acceleration hardware. Oh, the irony. But as I say, I still think this is a nice little example that's worth having a look at as an example of how to configure the blitter. So there we go. Now, the first thing to say is the data I'm actually using today is slightly different. This has actually been basically doubled in width here. Now, this is designed for when you're working with the blitter, when you're doing pixel shifting, you have to start using masks. And so this data has actually been doubled up to a full word width for each line to make that a bit easier to work with. So these aren't the same bitmap data as before. This is an extra export option on my Sprite editor that I've used. And you'll see we've also got a mask. These are 32-bit masks, as you can see, and they're just simply masking the 4-bit planes for the 8 lines of our tiles, and they're just masking a single byte. Now, this mask will be pixel shifted across along with the source data and the screen data to allow the per pixel movement for the moving sprite objects. So that's what this is for. Now, if you've missed the previous Mintile example, I should point out that when you see these large sprite objects moving across the screen, these are actually made up of a combination of 8x8 pixel tiles, which is why they're so slow. The reason I do that is this is multi-platform code. I've ported it to a lot of systems. By having a piece of tile code also do simulated sprites, I only need to port one piece of code. It's a lot faster. And if you're trying to port again to large numbers of systems efficiently, using as little time as possible, you want to try and minimize things, and unfortunately that means sacrifices on a lot of the systems. And in this case, it's meant that the example is too slow for the blitter to work effectively, which is a shame. Anyway, let's take a look at the code that we're using today, and let's see what it does. So basically, we're always working with our screen memory, and the screen memory is set up in bit planes. All of the bytes of one bit plane across the screen are in a single block, and then we move down 40 to move to the next bit plane. And so if we move down 160, we skip all 4 bit planes and move down to the next pixel line. Now, that said, we are calculating the screen base for when we're drawing our tilemap. Our tilemap is 32 by 24 tiles, so 256 by 192, and that is offset by 4 blocks to send to the virtual screen there. And that's what we use as the destination destination memory address when we're drawing the entire tilemap. But when we're drawing sprites, well, then we need to actually calculate a screen destination. So basically what we've got is we've got somewhere, where is it? This get screen pos function here, and it's the same as last time. It's calculating the VRAM destination based on the XY coordinate in D1 and D4, not D1 and D2. That's a typo from an old version of the code. And so basically this is calculating the byte position, which is why we are losing some of the bits of our X coordinate here. The X and Y coordinates are in pairs of pixels, not individual pixels. Again, that's about compatibility with the 8-bit systems. We can only have byte coordinates on those systems. And the 256 pixel wide screen needs to have an invisible area for the cropping function. So we use a 128 logical unit widescreen and a 96 logical unit tall screen. So that's why we're doing that. Now the important thing about the get screen pos here is the only thing that's changed is D1 and D4 are now being protected by this push and this pop here onto the stack, and that's so that we've got the original X and Y coordinates. We need that X coordinate for the per pixel movement later to calculate the shifting function. Okay. Now, the actual drawing of all of the objects, be it the screen, the tile map in the background, or the little sprites, is always done in strips. So we chop them into horizontal strips and do each one at a time. And it's the do strip routine that does that. Say if you saw last week, you've seen all this before. It's exactly the same. It's how we deal with it once we've decided what we need to do. So we're loading in a tile here from the source tile map A2. There's 1 byte per tile. 0 has a special function. The background is actually a cache of changes. For the sprites, that's actually a transparent part. And so if we've got a 0 tile here, tile pattern 0, we're going to skip this tile. But otherwise, we're checking the tile clear flag. And if that is set to 0, we're going to do nothing. Otherwise, we're going to clear the tile we just read in back to 0. That's for the background tile cache, because once we've drawn the change, we don't want to do it again to save time. So that's what we're doing there. Now, we want to work out what our source pattern data is. Now, the data is 16 colors, but we've actually padded it to a full 16-bit width here. So we've actually doubled it up. So we are now using 64 bytes per tile. So we are logically shifting the source tile number, effectively multiplying it by 64. We're then adding the A5 register here, which is the address to the source pattern data within memory. And that is now our source data here. Okay, what we're going to do next is we're going to calculate our bit shift. Now, as I say, the logical units are in pairs of pixels, and so we want a value from 0 to 7 effectively, which is our pixel shift. So we're taking the bottom two bits of the logical unit X coordinate here, and we are basically moving those into the correct position for the shifter functions of the blitter. So basically, these registers here use these top 4 bits as the shifter here. Now, 2 of those bits are coming from here, and they are taking the bottom 3 of these bit positions here. But then the other one that we need to do is actually based on the VRAM destination. Basically, are we drawing to an odd byte or an even byte? And we need to set that shifter accordingly, because this always works in 16-bit blocks here. That's the way this code works, the blitter works. So that's why we're doing that there. We're calculating the final bit of the shift based on the VRAM destination here. And then what we're going to do is we're going to start setting up the actual blitter functions. Now, these have various memory addresses. We've got them all defined here. We've defined them as symbols here for convenience. So we've got something that makes some kind of sense when it comes to actually looking at what our code is writing to. Let's take a look then. So the first job that we've got to do is we've got to actually check that the blitter isn't already doing anything. As I say, if it's still running, writing to these registers will actually change the job it's currently doing. So that's simply not going to work. What we're doing here is we're testing bit 14 of the DMA con register here, and we're just going to branch if that's non-zero. That means that the blitter is still doing a job, and so we just keep looping there until it's finished. Once it has finished, we can start loading in our source data. Now, the way the blitter works is it performs effectively a mathematical operation with a total of 4 different parameters, sources and destinations, I should say. So we've got 3 sources and 1 destination, and we create a mathematical operation to define that destination D based on an A, B, and C source. Now, the logical operation we're going to use today is defined by the bytes CA. Now, these are defined in the bits here that are being sent to BLT con 0. Now, the parameters that we have 3 source parameters and 1 destination parameter, A, B, C, and D. Now, A is our source mask, and this is being used to keep part of the pattern and remove part of the background. B is our source tile pattern, that's the tile we want to draw to the screen. C is the screen memory, but this isn't the destination, this is the source screen memory for the parts of the screen that we want to keep. The blitter works in 16-bit words for its reads and writes, and so we need to keep parts of those words and write them back to the screen. And finally, D is the VRAM destination. Now, I mentioned before our test mask here. This is the mask that's being used to select just 1 byte of each of the bit planes of our source pattern data. So that is the A parameter that is being used in this calculation. As I say, B is our source pattern for our tile, C is our screen, and D is the destination, and they're all being defined here. Now, this calculation that we're using here, this CA defined calculation, is D equals A times B plus not A times C. Now, D is the screen destination and A is our mask. So what this is saying is when our mask is 1, when A is 1, we're going to use B, which is our parameter. But when A is not 1, A is 0, we're going to use C, which is our current screen data. So this is saying, the first part of this before the plus is saying, when the bit in the mask is true, use the pattern data for our tile. When the bit in the mask is false, use the existing screen data. And so this is keeping the screen data or keeping our tile, depending on that mask. And that's what's doing the job that we're doing of drawing our pattern to the screen there. There we go. We're setting the bit shift for B here. B is, of course, our source bitmap data in our pattern. And we're actually setting it for A here in this alternate one here. Now, the format is slightly different, but fortunately, at least the bits are in the same position each time. It's always the top 4 bits that we need to set there. Now, that has basically set the masks for the job that we're trying to do in the bit shift. But we also need to set the first and last mask for A, there as a word, and we're just setting those as all bit 1s there. That will work fine. Now, the next thing, almost the last thing we need to do, is we need to set the offsets. After we've drawn a line, we need to potentially shift our data of our sources and destinations by a certain number. Now, the masks, we don't actually need to change the way the masks are set up, so that is just a 0. We're just going to continue on there. Now, the source pattern, we're actually shifting back by 2. That's so it can compensate for the masking operation. We're actually kind of drawing more than we should, if you see what I mean, for this compared to the source data. So we're shifting back by 2 for that. And then we're adding 36 to the 2 VRAM addresses, the one that's the source for the mask and the one that's the destination. And that's to move us down a line after one 32-bit block has been written there. So that's why we're doing that. Now, finally here, what we're doing is we are going to start the BLIT by defining the size. And so we're defining the width and the height here for our single tile block, and that will actually then be written to the screen. That actually effectively setting the size actually also starts the job. So that has drawn now, or is in the process of drawing rather, I should say, because of the speed, drawing the tile to the screen. And then what we're doing here is we're incrementing our A6 VRAM destination. We're also incrementing our X position here, effectively moving across the screen by 4 logical units, 8 pixels to the next tile position. And then we're repeating for the next tile, exactly the same as before. That's how we are doing the unflipped pattern data. Now, how about the X flipped pattern data for when our character turns around? Now, to my knowledge, there's no way to get the blitter to X flip data. So what I've done is I've defined an alternate set of the pattern data here. This is the alternate pattern data, and I've put a pointer in the sprite settings for the characters moving around to point to that alternate pattern data. The normal pattern data is here, the alternate one is here, and this is only done on the Amiga. No other system has required this. I've always been able to figure out a way of doing it without that. But in this case, I couldn't figure out a way of getting the blitter to do it by itself. I don't think it's something it can do. So then what we're doing here at the start is we're building a lookup table which is calculating the bit equivalent of the XFlip version of a source byte here. So we're calculating every possible byte input and the XFlipped output for that byte into the lookup table here. That's what's going on here. And then what we're doing here is we are taking our source data, our unflipped data, and then we are building an XFlipped equivalent. Now, I could have done this in Sprite editor and just exported them all XFlipped, but every other system has calculated the XFlipped equivalent in real time or something similar to that, and so I thought it would be better to do it in software here, so we had an example. Now, once we've XFlipped the data though, actually the XFlip version of the line drawing routine is basically identical, give or take. we've automatically selected the reversed version of the pattern data before this is even executed. The only difference in this is rather than incrementing A2 after each tile's drawn, we're subtracting 1 from A2, decrementing it. Everything else is the same. Defining the draw routine job is the same because the source pattern data has been flipped, so the drawing job is identical, and everything else, as I say, is exactly the same as well. So there we go. I was slightly disappointed with this example. I put a lot of effort into it and it worked very well, but the performance is just not really up to the job. But as I say, with all the effort I'd put in, and being as it is a viable example of how to use the blitter to do a job that is tricky to get set up, I'd still wanted to do the tutorial. But as I say, I will be going on and doing the more advanced Maxtile, which is my replacement for Mintile for most purposes. It's far more advanced, it can do everything Mintile can, so hopefully there won't really be any need for Mintile. And as I say, I will be doing that in software using software shifts, which it seems there's more than enough processing power to do, because as I say, the CPU was actually waiting for the blitter in this example because the tiles are so small. Anyway, hope you've enjoyed what you've seen today. Go to the website, download the source code, have a go with it yourself and use it in anything you can. Thanks for watching and goodbye.